This video is about graphing quadratic functions using standard form. For our definition, let's start here, okay, and say for our discussion, we'll call a quadratic, which is a degree 2 polynomial function, written in this way: f of x equals ax squared plus bx plus c. We're going to call that general form. Now, there is some discrepancy on the names of these different forms. Different authors use different words to describe them. For example, some authors call here what we're calling general form standard form. Okay, so for now, just for our discussion, we're going to call this ax squared plus bx plus c general form, so we don't get it confused with what other authors call standard form, which is the following. A quadratic function of the form f of x equals ax squared plus bx plus c, which again we're calling general form, can be expressed in standard form, which we're going to refer to as the following. F of x equals a times the quantity x minus h all squared plus k. And we can go from one form to the other by completing the square, which is a process we now know. It looks a little different when we're not using it to solve an equation, but it's the same basic steps and process. And then once you get it into what we're calling right now standard form with the h and the k in it, that's actually a really convenient form for graphing a parabola. Mainly because the vertex of the parabola is directly given in that form. It's just the point h comma k. And then the coefficient a, which is out in front, will tell us something significant. If a is positive, then the graph opens upward. If a is negative, then the graph opens downward. And those are the only two options for a quadratic function that we'll be dealing with. Now, to graph a quadratic function in standard form, and let's recall, not to be confused with all these different forms here, we're referring to standard form as the y equals a times x minus h squared plus k. That's what we're calling standard form. To graph from that form, we're going to do just a few steps. First, identify and plot the vertex. Remember, that's just h comma k. Once we have the right form. Secondly, we're going to plot a second point near the vertex by making a table or finding an intercept. And so we'll recall how to find an intercept. It could be an x or a y intercept. And then thirdly, we'll possibly need to use some symmetry to plot a third point and draw the parabola. 3 points is plenty as long as they include the vertex and then some symmetric points. Let's try an example where we want to express the quadratic function in standard form and graph it. Also, we want to state the domain and range using interval notation. So there are a few different tasks going on in this problem. Our first example reads this: f of x equals x squared minus 4x plus 6. Now, this given function is what we would call general form. And of course, we want to put it in standard form and then use that form to graph it. Now, as we said in our notes above, you can go from general form to standard form by completing the square. So we're going to do that, and let's rewrite our function. F of x equals x squared minus 4x. But then in the process of just copying down our function, instead of putting the plus 6 there, I'm gonna put a plus blank and then a minus blank and then a plus 6. Now that may seem a little weird, but let's go ahead and discuss how we can complete the square to go from general form to standard form. To complete the square, as you may recall, we look at the b value, which in this case is the -4. It's the coefficient of the plane x. And we want to add b over 2 squared. So let's recall b over 2 squared. And normally when we're using the completing the square process to solve an equation, we actually add this value to both sides of the equation, but that's not what we're doing right now. So we're still going to find b over 2 squared. Of course, b is negative 4, so that's negative 4 over 2 squared. Of course, negative 4 over 2 is negative 2 squared, which would be 4. So again, typically when solving an equation in this method, we would add 4 to both sides of the equation. But right now, we're trying to just change the form of our quadratic function. So what we're going to do instead is this. I'm going to add 4, the b over 2 squared value we just figured out, but then I'm going to subtract it right away. Now, that may seem a little ridiculous, but the whole point is we can't actually change the function, but we really want to add this 4 here in order to complete the square. So by adding it but then taking it away, I'm actually not changing the function and yet still getting what I'd like. Now our next step in completing the square is going to be to rewrite our function. So we'll say f of x equals, and then this trinomial that we've now created by adding the 4 is the perfect square, and so we can factor that as x minus 2 squared. That represents, again, just the trinomial there that's showing up as x squared minus 4x plus 4. But then don't forget, we have this minus 4 and plus 6 at the end. We had to put the minus 4 there to counteract the 4 we added. So the minus 4 is now actually part of our equation, and so is the plus 6, which was there originally. We'll just combine those terms. Minus 4 plus 6 is really plus 2. And now magically what we have is a quadratic function that's in what we're calling standard form. Now, if you look back up at the standard form, you'll notice that when you see x minus 2 in parentheses, as we have all squared, that 2 represents the h value. And then when we see the plus 2 at the very end, that represents the k value, which tells us some important things. First of all, our vertex is the point h comma k, which would be 2 comma 2. Observe here briefly that when you see x minus h in standard form, notice ours says x minus 2, but then when we use the vertex form, or the vertex point, we use just the 2, not the minus. So in other words, the vertex coordinate, the x-coordinate, is always the opposite of what you're looking at in standard form if you're looking at the sign in front of that number. So we saw a negative 2 in standard form. We're using a positive 2 for our x-coordinate of the vertex. Now, as we mentioned above, to plot a parabola, we can start with the vertex. So let's go ahead and plot the point 2 comma 2. Let's also recall that, as our note said, the a value, which is the ones in front of the parentheses, notice we don't see anything there in this example. That means that a is actually 1, because a 1 wouldn't show up if it was in front of those parentheses. If a is positive, that means this parabola is opening upward. So let's just make a little note here. A is positive, which means we're expecting an upward opening parabola. We know the vertex as 2, 2, so now we'll just go ahead and follow the rest of our step, which is to find another point surrounding it. Now, think about this for a second. If you look over at our graph, where I have plotted the point 2, 2, let me just draw a sketch of a parabola opening upward through that vertex. Now, that's not our final graph, and I don't know if ours will look exactly like that, but it'll look something like that because we know that our graph should open upward, and that's its vertex. Well, just look at this very briefly and realize that this parabola is not going to intercept the x-axis, right? If it starts above the x-axis where the vertex is and opens upward, it's not going to hit the x-axis, which means there is actually no x-intercept for this graph. Now, that's fine. That means we shouldn't go looking for one in order to add some more points to our graph. So that means maybe we should look for a y-intercept in an effort to find some more points. Remember, just a vertex is not enough. We need some other symmetric points. Now, to find a y-intercept, we're going to set x equal to 0 and solve. And so if you go to our standard form we've been using here, we want to find f of 0. Plugging that in for x, that would give us 0 minus 2 in the parentheses. That's negative 2. Squaring that would give us 4. and then we'll add 2 to get 6. So if f of 0 is 6, that means the point 0, comma 6 is on our parabola. So let's go back to our graph. I'm going to erase the general sketch I threw up there just to recognize where this parabola is opening. I'm going to leave the vertex point 2, 2, and now plot the other point 0, 6. So 1, 2, 3, 4, 5, 6. We know that point's on our parabola, and then we're going to use some symmetry to find a third point. By symmetry, we mean this. There is a vertical line that's not always visibly part of our graph, but it always goes through the vertex in any parabola. And any parabola is symmetric about that line, which means if I were to fold my graph on that line, the parabola would land right on top of itself on the opposite side. So that means if I have the point 0, 6, that is 2 units away from that line of symmetry, that means I'm going to go 2 units on the opposite side, same elevation, and put another point. That would be the point 4, comma 6, and we know it's on the graph because of symmetry only. Now, I'm going to connect these 3 points I have to form the basic shape of a parabola. Artistry isn't the goal here, but accuracy is, so we'll make sure our points are labeled clearly, and there we have our parabola. Now, as part of this problem, we also wanted to state the domain and range in interval notation. So we'll go ahead and do that. Now, the domain pertains to x values the graph uses. As you can tell by the arrows, though this graph is going upward to the left and the right, it is going left and right, and the arrows mean it keeps going that way forever. So our domain, given that there are no hop, skips, or jumps or problems in this one, is going to be negative infinity to positive infinity, which actually is the domain of every quadratic function. So that should make things easier for us. And then our range has to do with the y values being used. Now look at our graph. You can pretty much tell right from it that the graph is going up forever thanks to these arrows, but then it goes actually no lower than this vertex point, and we'll recall that was the point 2, 2, which means our range is going to go, as we express it, from low to high. The lowest point it hits is a vertical value of 2. That's the y-coordinate of the vertex. We know it actually hits the point there, so we put a square bracket around 2. And then it goes up forever, so we'll say comma infinity with a parenthesis there. And so there's our domain and range. Let's consider a second example in these same instructions. This one reads f of x equals 5x squared plus 10x. And again, we want to turn this thing into standard form and then graph it and find the domain and the range. Now, this one, when you compare it to the first one we just did, is almost in the same form. It's almost in the general form we've been discussing, except notice there's no c value if you're comparing it with that form in this example. That's fine. That doesn't really change a whole lot. But also notice one more significant difference, which is that there is a coefficient in front of the x squared variable here. So there is 5x squared, and that 5 being the leading coefficient will affect things as we go. So with the function being 5x squared plus 10x, we want to start by completing the square. Now here's the deal with this leading coefficient of 5. We actually don't want it there when we complete the square. So we're going to do a little secret trick, which is to factor it out. Now we would write the 5 being factored out, and we have to factor it out of both of these terms. So when I factor a 5 out, that would leave me in parentheses with x squared plus 2x. Then I'm going to put the plus blank in order to complete the square, but I'm going to put that blank inside the parentheses that we've used to factor out that 5. Okay, so that's where we just have to be really careful about compensating by adding the blank, and then remember we've been subtracting something else as we did in the first problem. We have to add and subtract to maintain the exact same equation. But let's be careful here. Now to add something, we're going to add the b over 2 squared. B is 2, so b over 2 squared is really 2 over 2 squared, which is really 1 squared, which is 1. So I'm going to add 1 in my blank, but then be careful here. I can't just subtract 1 to make this all better, because I actually didn't just add 1 by putting a 1 in that blank. You see, remember we factored this 5 out way in the front? That 5 is really being multiplied by all of these terms in the parentheses, which means that 5 would get distributed now to this 1 that we just added there, which means we really added 5 times 1 to this overall equation, which is 5. So I have to subtract 5 in order to make up for that. So just be extra careful with that step in particular. Now let's proceed with the factored form. We'll write this as f of x equals 5 times x plus 1 squared. That's factoring the perfect square trinomial we've now created in our problem. And then don't forget our minus 5 there at the end. So now this is in vertex form. We can tell what the h and the k are and pick them out for our vertex. Remember, the h is always the opposite of what you see in the parentheses, so we're going to call that -1 for our x-coordinate of the vertex. And the k is just whatever you see hanging on the end or the beginning being added or subtracted from it, so we'll say -5 for the k value. So our vertex will be -1, -5. That'll help us get started with the graph. We'll go ahead and plot that. Our next step would be to find some other points surrounding the vertex. Now we've discussed already that often intercepts are nice points to use for those. Let's now look back at our equation and recall that in the front of it, remember we factored out this 5? Okay, that would be our a value. So we'll say a equals 5. And importantly, that means a is positive, which means this graph is, you guessed it, opening upward. But if it opens upward through the point with a vertex of -1, -5, that means it actually would hit the x-axis somewhere. Now, we don't know exactly where yet, but my point is, it's not a bad idea to try to find the x-intercepts in this case, because we know there should be some. To find x-intercepts, we'll go ahead and just set y equal to 0. And we can do this in any form. We'll go ahead and use our standard form that we've created. Setting y equal to 0 means like setting f of x equal to 0. So we'll say 0 equals 5 times x plus 1 squared minus 5. And then we want to solve this for x. Now this is just a quadratic equation, and we want to start by perhaps adding 5 to both sides, which would give us 5 equals 5 times x plus 1 squared. And then we can divide by 5 on both sides to get rid of these 5s. That would mean we have 1 equals, and then 1, or you don't even have to write it, 1 times x plus 1 all squared. Now we want to try to solve for x. As we've seen, we can do this by the square root property, which would involve us taking the square root of both sides of our equation. But don't forget we have to have this plus or minus when we take the square root of 1 on the left side of our equation, which means ultimately we have here plus or minus 1 equals x plus 1. Now we want x alone, so we'll subtract 1 from both sides, meaning minus 1 plus or minus 1 would equal x, and that means we have two options. So x could equal -1 plus 1, which is 0, or x could be -1 minus 1, which would be -2. So that means we have two places for x-intercepts. We can go ahead and plot our intercepts at those places where x is 0 and where x is -2. Now this is fitting with what we were discussing earlier about a parabola that opens upward. We already know the vertex is plotted. And given these x-intercepts, this is going to tell us that it's a pretty narrow looking parabola. We can go ahead and graph it at this point using these 3 points. We know it's some kind of curved U shape, somewhere between a V and a U, opening upward, hitting the vertex point -1, -5, and hitting the intercept points, which are -2, 0, and 0, 0. So there's our graph. Now we can also discuss the domain and range. Recall the domain of any quadratic is all reals. That'll save us a moment. We'll just write that in. And then the range pertains directly to which way this parabola is opening and where the vertex is. Notice it seems to go no lower than -5. That was the y-coordinate of that vertex, but it uses that point. So we'll say bracket on -5, comma, and then so that's the lowest point. The highest point, thanks to these arrows, would be infinity. So we'll say -5 to infinity, and that would be our range. So we have domain and range, we've plotted our parabola, and we've turned it into standard form as well. Let's try a third example, same directions here. We want to turn the following function into standard form and then graph it and so on. our function reads f of x equals negative x squared plus 8x plus 4. Now, this function is a little bit like the one we just did in that there is a leading coefficient in front of the x squared that's not just 1. It's this, in this case, it's negative 1 due to the negative sign in front. So, like we did before, we don't want that negative sign there. We'd like to factor it out. So let's rewrite this function as f of x equals, and then we'll put a negative sign there, factoring it out then with some parentheses, which would leave us with x squared. But then it would be a minus 8x after that, because if we're factoring a negative out, you can always kind of check by distributing it back in. This would be negative x squared, and then negative 8x would be the plus 8x that we see in our original function. So just be careful with the signs on this kind especially. And then we're going to put our plus blank inside the parentheses like we did before. We're going to ignore this 4 for a second like we did in the first example and actually kind of push that outside the parentheses. So I'm going to say here minus blank and then plus 4. So we have to keep that plus 4 in play, and we have to subtract whatever we're adding in order to compensate and not actually change the problem. So let's keep all these things together as we proceed. We have to add b over 2 squared inside to complete this square. Well, b is negative 8. That over 2 would be negative 4. Squared would be 16. So I'm going to put a 16 being added in with the trinomial to complete the square. But now remember, this negative sign that we factored out would be distributed to everything inside the parentheses, even that number we just added in, the 16. Which means we really added negative 16 overall to this function. If I just put in a negative 16, I have to take it away. But how do you take away a negative 16? Well, you add 16. So we're going to actually turn this into a plus 16 for that compensating blank. And then we have the plus 4 after it. Now that we've completed the square, let's go ahead and rewrite our function in factored form. This would be f of x equals, keep the negative out front, and then if we factor the perfect square, we'll end up with x minus 4 in parentheses squared. And then on the end, we had this plus 16 plus 4, so we'll just call that plus 20. At this point, we can pick out the important information from our function, which is in standard form, and know that the vertex, remember being h comma k, it's going to be the opposite that we see in the parentheses for the h value. So when we see x minus 4 in there, we're going to call that a positive 4 for the h value. And then the k value is 20. That's what we see on the end, which means our vertex is the point 4 comma 20. Now with a y value of 20, we're probably going to have to adjust the scale of our grid. The same grid we've been using for the previous examples won't quite do it. I need to be able to see and get up to a 20 in my y scale easily. So you could count by, well, depending on how much graph paper you have, I mean, maybe go by 2s, maybe 4s. In this case, let's go by 4s. It will make it convenient because our x coordinate of the vertex is 4. You could go by 4 or 5, anything that will get you to 20 fairly enough and yet remain readable. So if we go by 4s, that means every grid mark is going to be 4, so we'll call that 4, 8, and so on. That means 5 grid marks would give me up to 20, which is how high I have to go to plot this vertex. So 1, 2, 3, 4, 5 grid marks up there would be 20, vertically speaking. My vertex is at the point 4 comma 20, and again, if I keep the same scale for the x-axis, where one grid measures 4 units, that means I'm going to put a point right at 4 comma 20 for my vertex. Now, also look back at the form we've come to here, our standard form, and notice that the a value is negative 1. It's what that negative sign that we factored out way in front of the parentheses. That means in this case a is less than 0, which means, as our notes said, this parabola is opening downward. Now that's good news for our graph because we're already starting with a vertex that's high up, and it's going to help us visually to be graphing something that's opening downward. And if it opens downward, we'll figure out exactly how in a second. And again, that means that it's going to hit the x-axis since it's starting above it and opening downward, which means there should be x-intercepts, and we can go ahead and find those by setting the y value, or in this case f of x, equal to 0. So let's try this here as 0 equals negative parentheses x minus 4 squared and then plus 20. We can solve this by subtracting 20 from both sides. That would give us negative 20 equals negative x minus 4 all squared. And then we can cancel these negatives simply by dividing by negative 1 on both sides. That would give us 20 equals x minus 4 squared. Now we'll do our square root property and take the square root of both sides. Okay, so let's not forget our plus or minus. The square root of 20 can be reduced. 20 is 4 times 5, which means this would be reduced to 2 root 5. So plus or minus 2 root 5 equals x minus 4. And then, of course, to get x alone, we'll go ahead and add 4 to both sides. That'll give us, for x-intercepts, the following values. X would be 4 plus or minus 2 root 5. That's by adding 4 to both sides of our equation. Now, those are not pretty numbers, and so we're going to have to do a little bit of estimating. Let's crunch these x-intercept values on our graphing calculator to get an accurate enough estimate. We'll probably just round to the nearest tenth or something, but we have 4 plus 2 root 5 as an option, so we'll say 4 plus 2, and then in a TI-84 or 84 plus, you can just do 2 and then put the root right next to it, and then put 5 in the root. It will automatically multiply the 2 with the root there. And so we'll just hit enter, get an approximation as, now it says 8.472135. Okay, so we'll round it and just say 8.5. Now that was one value. Let's compute the other as well. That was for minus 2 root 5. So we'll go ahead and type that one in just the same, for minus and we'll call that value negative 0.5. So we want to plot these as intercepts. Obviously, we're going to have to round or estimate where we put these points. So 8.5, remember, every grid mark is 4. So 2 grid marks is 8. 8.5 would be just a little bit beyond that. So we'll just put a point just a little bit to the right of the second grid mark. And then negative half, just slightly left of the y-axis, would be our negative half mark. And so with 3 points gained by finding the vertex and then the intercepts in this case, notice, just observe that the intercepts are actually symmetric. If we were to put in our line of symmetry, they do appear to be equidistant from it. So we didn't use the line of symmetry to find those points, but we could have, as we did in that first example. So we'll go ahead now and graph our parabola, which opens downward and passes through the points we've already plotted. Now let's discuss domain and range. Recall the domain of any quadratic function is all reals. So we'll say negative infinity to positive infinity. And for our range on this one, notice this parabola opens downward, which means the lowest value it's going to hit is negative infinity. It doesn't actually hit that, but it goes down forever. So negative infinity is the lowest y area, and then going upward as high as the vertex in this case. That coordinate we already discussed as 20. It's going to use it, so we put a square bracket, which means that's our domain and range.